All right. This is lecture 18. We're going to talk about magnetic force. Last two lectures we've covered what magnetic fields do and how to calculate them, but we haven't let them do anything because we haven't had, they haven't been able to exert a force, so they can't move things around. So, my number of the day today is actually from Mythbusters. I was asked to do a talk once in one of the dorms where they wanted to use university money to go skydive. And so they needed to have some scientific content, so they wanted me to come in and talk about skydiving. And so I need to know, how fast you have to be going when you hit the ground and hurt yourself. And I didn't have this number, but this Mythbusters turned up with it. So for a minor injury, a break or something, 25 feet per second or 17 miles per hour, or 7.6 meters per second. And for major injury, up to and including death, 50 feet per second, 34 miles per hour, 15.2 meters per second. We're working on Maxwell's equations. We have been all semester. We're making a lot of progress. Maxwell's equations cover how fields work. And so we've got Gauss's law, which is complete. No magnetic monopoles. The flux out of a closed surface, magnetic flux out of the closed surface is zero. Faraday's law, which isn't complete, then we have a piece missing. And up to now, Faraday's law has been called independence of path. Ampere's law, which we worked on last time, which also has a piece missing. And then to have Maxwell's equations do anything, we need to know how the fields exert forces on charged particles. That's given by Lorentz force, where we have the force is QE plus something, and we get that something today. The magnetic force is Q, velocity, cross, field. So the magnetic force on a particle, first it has that cross product, so it acts sideways, but it also depends on how fast the particle's going. All right, we clean this up. Okay, so the Lorentz force. We have two forms. We had two sources of magnetic field, either just particles moving in space or particles moving in a wire. We'll have two forms for Lorentz force. First, we're going to focus on the magnetic part of force now. QV cross V, so this is particle form. Now, if the force is on a current moving in a wire, we have to look at a little bit of the wire, so we get the differential force. So IDL cross V, this is the current form. And this is the current, and this is a path element, a little chunk of the wire. And likewise, this is the velocity. And the charge of the particle. All right, so we've probably done enough integration to last you guys forever. If we let the field be uniform, and we let the wire be straight, so if the field is uniform, and the wire is straight, the force on the wire is the current, the vector L across the field, and this vector L is just a vector from one end of the wire to the other. And you can see we get that just by integrating that, those assumptions make everything constant. We leave these up. There's a couple of properties of magnetic force. First, the magnetic force on the stationary charge is 0. This lets me write great exam questions, right? To make this insanely complicated magnetic system, put a charge there that's stationary, and ask you the force, and you guys will happily calculate for an hour, but the answer is 0. All right, so that's a little weird, because certainly the electric force in the stationary charge wasn't 0. Even weirder is the magnetic force does no work. Which was nice. It means we have no magnetic equipotential, so because the way we got from potential energy to from field to potential energy was through the work. And if you look at this, the power is the work per time, is the force, F dot dr is the work, T is the force dotted with the velocity. But because of this cross product, the force and the velocity are right angles. And if you dot two perpendicular vectors, you get 0. So, the magnetic field does no work. Anytime you see work done, that means it's got to be the electric field getting it done.